Good evening. My name is Herb Moyer. I'm a 50-year resident of Exeter, UNH graduate, and former Exeter selectman. And we're here tonight with Professor Emeritus, UNH Professor Emeritus Barry Rock. And I'll introduce him in just a second, give you some of his curriculum vitae. But we're here to share with you a three-part series on climate change. Tonight's program is the politics, climate, and the future. And Professor Rock is a faculty fellow in the Office of Engagement and Faculty Development and has recently served as co-chair of the UNH Writing Academy. Dr. Rock is a professor emeritus in the Department of Natural Resources and the Environment. He received his BA in botany from the University of Vermont and both his master's and PhD degrees in botany from the University of Maryland. Following the receipt of his doctorate, Dr. Rock held the positions of assistant and associate professor of biology at Alfred University in New York. In 1978, Dr. Rock became the site botanist for the joint NASA GeoSat remote sensing study conducted at Lost River, West Virginia. In 1987, he joined the faculty at the University of New Hampshire as an associate professor of forest resources and with the Institute for the Study of Earth, Ocean, and Space, what we call the EOS Institute. Dr. Rock's research and publications have focused on remote sensing of vegetation, specifically on basic and applied research dealing with biophysical properties of plants, pigment concentrations, anatomical characteristics, and moisture content of leaves, and their influence on reflectance features which may be remotely detected from space. During the 1994-95 academic year, Dr. Rock assumed the position of senior scientist and assistant director of the GLOBE, Global Learning and Observation to Benefit the Environment program, an environmental education outreach project directed from the White House. Dr. Rock developed the hands-on science activities to be conducted by the GLOBE students on an international scale. There were 26 participating countries involving over 2,500 schools. GLOBE was patterned after ideas presented by Al Gore in Earth in the Balance. Between 1997 and 2001, Dr. Rock coordinated a New England regional survey of climate change impacts to the region, both over the past 100 years and those projected for the future. Dr. Rock, welcome to our program here at the TV station at Exeter. Welcome.
Herb, it's a pleasure and an honor to be here, and I look forward to discussing the science behind climate change, as well as some of the activities that people can do to address the issue of climate change. So thank you very much for having me here.
Excellent. And we have a pre-recorded several weeks ago program that you will see Barry Rock presenting, and then we'll have questions and answers afterwards. If you would simply have a question, put it in the Q&A section and we'll address it. We have a few questions of our own to pose to Dr. Rock, and we'll go on and enjoy it. We hope you can join us for the other two sessions on March 2nd at 7 and March 9th at 7. All right? Very good. Thank you.
Good evening. Today we want to discuss climate change, the politics of the present time, and kind of consider where we want to go in the future. Maybe not where we want to go, where we will go in the future. So, I just love looking at the Earth from space. This is an image that was taken by one of the Apollo astronauts returning from the moon. And what was striking was the difference between the moon and the Earth. The moon is just like plaster of Paris, gray, dull, boring. Earth, on the other hand, as we see here, is so spectacular. And one of the messages I want to leave today is that there isn't another planet like Earth. There's no planet B. And so we really need to be very protective of this big blue marble. It's spectacular. Today we want to talk about the science of climate change. And I want to emphasize that within the scientific community, there is no debate. Climate change is very real. And the real challenge is educating the public and engaging the public in doing something about climate change. We'll talk also about the political climate in both the Trump era and then the post-Trump era. We'll talk a little bit about recent climate change and variability impacts, and then we'll finish with a brief discussion on where we go in the future. First, let's talk about some of the terminology. Weather versus climate. I think probably most of you recognize there is a difference, but weather is what happens day to day, week to week. Climate is what happens over the period of a year or more, decades. So it's a timing thing. And we can think of a summer climate here in New Hampshire and a winter climate here in New Hampshire. We also have summer and winter weather conditions, but those are temporal and temporary. The idea of a theory versus a hypothesis. I think we tend to think of theory as being rather theoretical. However, in science, a theory is the accepted concept supported by a wide body of data, facts, and that sort of thing. A hypothesis is an educated guess, what we think may happen in the future. And so when we talk about a climate change theory, it's solid because the data just support that particular view. Opinion versus peer review process. In science, the peer review process is where if I write a paper for publication and I want to publish it in Science or in Nature or something like that, the first thing that will happen is the editor of the journal I want to publish in sends it out to 5 or 6, maybe 8 or 10 other scientists that are expert in the same field I'm in. And they decide whether it is to be published or not. So peer review is a very formal process that is very typical of science. Opinion, on the other hand, anyone can have an opinion. And unfortunately, the public doesn't necessarily make a distinction between an opinion, they kind of treat it as fact, versus the peer review statement from a scientist. Then we've got the belief system versus scientific fact. Very often you end up hearing people say, well, I don't believe in climate change. That's sort of like saying, I don't believe in cancer. Cancer is cancer, and it doesn't really matter whether you believe it or not. If you've got it, it's a serious issue, and hopefully you do something about it. And the scientific fact is based on, again, this peer review process, this idea of very strong scientific consensus. So, is there a strong consensus among scientists at this point that climate change is caused by humans? And here you see this graphic. Turns out between the years of 1991 and 2012, so a good long period of time, a total of nearly 14,000 peer-reviewed journal articles were essentially reviewed in the sense of was there an addressing of climate change as a fact, as an issue that really isn't being debated. And of those nearly 14,000 articles, only 24 rejected climate change, climate warming caused by humans. And when we look at that, then, it turns out that 99.8% of the knowledgeable people in this area accept an anthropogenic cause for climate change, a human cause for climate change, and only 0.2% don't. So that's a pretty strong consensus. Let's talk about some of the drivers, some of the causes of climate changing. You can see in this graphic that there are 5 factors that are considered. One would be heat-trapping gases. Those are the greenhouse gases. We'll talk more about those shortly. There's solar output. There are times when the sun is putting out a lot of energy, tends to have a lot of sunspots on its surface, and there are other times where the sun is more quiescent, quiet, and not putting out as much energy, and that clearly affects our climate. Aerosols from volcanic venting. These would be essentially small liquid droplets. They will reflect sunlight back into space. Think of it as a haze, if you will. And that's a factor. And then aerosols from urban pollution, that's a big factor. And then land use change. If we cut our trees down and do that on a very large scale, that can affect the climate. And so we see in this graphic, perhaps the thing that shows up most obviously is this blue thing that almost look like icicles. And the vertical axis, this is 0, no change, and then upward would be increasing changes, and downward would be decreasing changes. And the blue line, that's the aerosols from volcanic venting. You may not have thought of that as a significant issue. The greenhouse gases are this rising line here. And then this orange line, little peaks and valleys, that's the solar sunspot cycle, essentially an 11-year period. And you can see that that has an effect, a positive effect on our climate. And you can also see the urban aerosols here having an effect of cooling. Okay, it turns out that those icicles are volcanic eruptions. The time frame of volcanic eruption. I think most of us can remember Pinatubo over here. Some of us remember Mount St. Helens. I remember it very, very well. You probably never heard of the volcano Agun. That's in Bali. This is Mount Pele, that's in the Caribbean. This is Krakatoa in Indonesia. And you can see some volcanoes cool more than other volcanoes, and Krakatoa was a biggie. It turns out that prior to Krakatoa in 1816, there was another volcano, a larger one called Tambora, and we'll show you what the effect of that was. Notice that this period from about 1910 to 1960, we didn't have volcanoes, or at least a cooling resulting from volcanic eruption. And we don't know why that is. We don't control volcanoes. The Earth is in charge of that, and that is a period, about 50 years, where we didn't have a volcanic eruption event and we didn't have cooling. I want you to keep that 50-year period in mind, that 1910 through 1960. Okay, here's the result of Tambora. Tambora created something called a year without summer all across New England. It snowed every month of the year. Can you imagine that? And that was because the volcanic eruption put all of these volcanic aerosols into the atmosphere. They reflected sunlight and the sun's warming energy back into space, and it cooled the place dramatically. So this is just a dramatic image of poor people trying to figure out what to do. Let's think of this as the month of August, and they've had snow. Glad I wasn't around back in those days. Turns out that variation in solar activity is important, and there have been a total of 24 cycles, that 11-year period, and we're going to show you a graphic of that shortly. But it turns out in cycle 24, which is the most recent cycle, we're now entering cycle 25, in the cycle 24, we had periods when there was a very active sun. You see April of 2014, lots of sunspots, more energy coming from the sun. And then we had a quiescent sun, a quiet sun, December of 2019. Few, if any, sunspots. The sunspots we see here, each of these things that we maybe think of a sunspot as kind of a dark area on the sun, it's really a massive explosion called a mass coronal ejection, and huge amounts of energy blasted out by that. But when you don't have sunspots, you don't have that massive outpouring of solar energy. This graphic shows us the sunspot cycling period starting back in 1609. Can you imagine who it was that started that study of the sun and looking at sunspots? It was Galileo. And so you see over here the first peak. Galileo was measuring that. He didn't, that wasn't a good idea. It was bad on your eyes. You can see that other scientists weren't studying the sun at that point. This is called the Maunder minimum, and it's not clear what the Maunder minimum was caused by, but it was a long period of time from about 1660 to early 1700s when there weren't sunspots. And it's not really clear from a historical standpoint if that is because other scientists knew that Galileo had been excommunicated from the church, was under house arrest, that sort of thing. And maybe they were studying sunspots, but boy, they didn't want to tell anybody about that. However, real monitoring begins here in the 1750s or so, and you can see that this is an 11-year period from one peak to another. This is a period where there was prolonged cold. And again, we don't control what's going on the sun, so we don't know why those were very weak solar cycles in the 1800s, early 1800s, but they happened. And then we see a longer period of essentially a cycle, essentially a 100-year period, like so. I just mentioned down here that period in the 1800s when things were pretty cold, and then 1915, again, kind of the shallow or the weak solar activity. That turns out to have been when Shackleton, in his Antarctic expedition, ran into huge amounts of trouble, ship being trapped in ice for months, and they had to end up eating sled dogs and things like that. So clearly, changes in terms of solar output have an effect here on Earth. Then we have this period from 1900 to about 1960 as each solar cycle got bigger and bigger and bigger. And again, we don't know why that happened, but it happened, and we'll keep that time frame in mind as well, the 1900 to 1960. This is where we are essentially today. Over here is cycle 24. I said that's where we are now. We are actually beginning cycle 25 in 2021. And it's interesting, this is a fairly weak 11-year period solar cycle, cycle 24. Not nearly as forceful and impactful on the Earth as cycle 22 or 23. Turns out that cycle 24 was the weakest in 100 years, actually a little more than that. Now, this is what is predicted for solar cycle 25, and it's predicted to be weak again. And I just drew a line across the projected peak for cycle 25 and then the actual peak for cycle 24. By all rights, it should be getting colder on planet Earth based on solar cycle activity. So keep that in mind. I now want to go to looking at greenhouse gases and the patterns of greenhouse gases, in particular carbon dioxide. This is the Mauna Loa Observatory on the Big Island of Hawaii, and they have been making measurements since 1958. The idea of going out to Hawaii to make these measurements was a fellow named Keeling, David Keeling, wanted to see what sort of the background level of CO2 was far away from any industrial sources as possible. So he selected to do that on the island of Hawaii, and he was shocked to find that it wasn't stable. It wasn't a flat line. It was increasing. And more interestingly, it wasn't just a straight line of increase, it was little peaks and valleys, peaks and valleys. This was a surprise. This was not anticipated at all. And because it was happening, it was decided to continue this measurement, and it's ongoing today. Turns out that back when I was in high school, and I was in high school in 1958, I was between sophomore and junior year in 1958, and back then the amount of carbon dioxide in the atmosphere globally, but also on Mauna Loa, was about 320, and that's parts per million. And I know that sounds like a very small amount, but parts per million of carbon dioxide, a greenhouse gas, is more than enough to keep our planet habitable. I mean, carbon dioxide is a very good thing because it is a greenhouse gas. It absorbs solar energy and then re-radiates it out. We couldn't live on this planet if we didn't have greenhouse gases such as carbon dioxide, methane. There are several others. They're called trace gases because they're only 1%, actually less than 1% of the atmospheric concentration. The greatest gas in our atmosphere is nitrogen. Oxygen is the second, about 21% of oxygen. So the greenhouse gases are a very small number of gases, and in parts per million, they make the planet habitable. I've indicated here the 400 parts per million. There was a time when I first started at the University of New Hampshire, we didn't think we could reach 400 parts per million. I arrived in the university in 1987. And so it became a shock to me and to many others that not only had we reached 400 parts per million, but we've gone over that. And we're going to reach 420 in the year 2022. So, and that again is because we just keep pumping carbon dioxide into the atmosphere largely from the burning of fossil fuels. So let's look at those little peaks and valleys. They're really interesting. It turns out that each peak ends up being in the essentially the beginning of summer. Each of the valleys ends up being the end of summer. And what this shows very, very nicely, quite dramatically, is the effect of vegetation. Remember that vegetation is absorbing carbon dioxide from the atmosphere, and if over the fall months and on into winter, we get here to May, the leaves are coming out. And wow, when those leaves come out, it would be wonderful if we could hear it. There would be CO2, carbon dioxide, being taken in by the leaves. There would be a big sucking sound when those leaves come out and start photosynthesizing, start absorbing the carbon dioxide from the atmosphere. And then, of course, we get down here in September, and the leaves have lost their chlorophyll. And so that sucking sound goes from down to, so again, the importance of vegetation here and importance of forests. Okay, and again, that line showing that we had passed 400 parts per million. So that's the greenhouse gas. Now let's talk about the impact that has had on essentially the temperature. And this is a graphic showing annual temperature between 1880 and 2020. And you might wonder why it starts in 1880. That's because by then a thermometer, an accurate thermometer, had been developed, and the first measurements were actually done at Dartmouth in Hanover. And we can see there's a pattern here where it was fairly low temperatures in the 1800s, the early 1900s. Remember that 1900 period when Shackleton got trapped in the ice? Well, that was a real low point in terms of annual temperatures. We then see a rise, and then we see a leveling off, and now this is where we are today. Very, very sharp rise. And the Intergovernmental Panel on Climate Change, the IPCC, recognizes factors that influenced that first half of the 20th century warming. That's over here, like so. And that is felt to be due in large part to natural processes. It would be solar ramping up. Remember, we saw that in the extended solar cycle period. And then we reach that period in the middle of the century where things kind of stabilize. And that was initiated by World War II and all of the aerosols that went into the atmosphere, making munitions and tanks and that sort of thing. And then that continued on through the 50s into the 60s. And that was considered to be a cooling that was man-made because we had produced those industrial aerosols. So again, man-made in the middle. And now we're in this latter half of the 20th century and on into the 21st century where we see dramatic warming, and that is attributable largely to those greenhouse gases, the GHGs. You can also see 2016 up here in the corner, right there. That's the warmest year on record. We're over here. Get the pointer. There we go. We can see there was a bit of a cooling, and now it actually is beginning to increase. You can pick out different years here. When I first started at the University of New Hampshire, 1998 was the warmest year on record, and that shows up over here. So there's no doubt that the planet is warming, and there really is very little doubt as to what the cause of that warming is. Turns out also, using our wonderful satellites, remember the last time we talked about monitoring forest health from space, all of these satellites can actually measure temperatures of the atmosphere in a variety of ways, and you can see an interesting pattern here. Turns out that the greatest amount of warming is in the northern hemisphere, and there isn't quite as much warming in the southern hemisphere, and that's in large part because northern hemisphere is where most people live, where most people are driving their cars. We've got the most factory emissions, you know, all of that. You might have thought the equator would have been the warmest, and it's clearly not. So again, the science is really firm on these kinds of factors that influence our current warming pattern. This again is 2016, and that again is the warmest year on record to date. Also turns out there are other kinds of greenhouse gases, and there's a great modeling activity underway trying to figure out what the normal warming or cooling would be without any greenhouse gases or factors like that, and then compare that against what we see. So the blue is natural only, solar cycles, volcanic eruptions, and that sort of thing. The red would be with anthropogenic forcings, and then the black line, see if I can get the pointer to work here, this black line is what is actually being measured. And you can see that without the greenhouse gases, we would be pretty stable. You see that here. But with the greenhouse gases, we're going off the chart, so to speak. Now, at the University of New Hampshire, we have an ice core analysis group. Here is a team at the Vostok Center in Antarctica, and they're holding ice cores. Those long pole-like structures are ice cores. Each of those cores will then end up being cut into smaller pieces, sectioned, and then studied. And the reason we want to do that is that these ice cores contain bubbles of atmosphere, and those bubbles, depending on the length of the ice core, go back millions of years. And so this is fossil air trapped in this particular ice core, section of an ice core, and you can see the little bubbles in there. See the little bright spots? You can also see there's an annual cycling. When in Antarctica we reach summer, there's a fair amount of dust in the atmosphere, and it ends up getting trapped in ice. And so it turns out we can measure back millions of years what the atmospheric concentration of CO2 was. And that becomes very, very valuable to understand what changes are today versus a long period of time. Here are some of the other greenhouse gases. You see carbon dioxide, but you also see methane, see nitrous oxides. All of those are part of that 1% of trace gases that keep our planet comfortable, habitable. And you see each of those rising dramatically following the Industrial Revolution. Okay, this is from a European project. It's called EPICA. They are coring ice cores as well in Antarctica. And what we see here along the bottom would be going back essentially 650,000 years and then on to the present. That's where we are today. The blue lines are carbon dioxide concentrations. The white lines are oxygen concentrations. But we want to focus on the greenhouse gas carbon dioxide here. And this is parts per million, going from 180 parts per million up to 300 parts per million. Remember, we've gone over 400 now, so really off the scale in terms of what has happened in the past. And this is useful information because it gives us an idea of what the historic range of natural variability is, and then we can compare that with our anthropogenic, our man-made range of natural variability. I refer to the upper yellow line here as a ceiling, and here would be the floor of natural variability. Each of these peaks, this is one single glacial cycle, about 110,000 years in length. We're currently in what's called an interglacial, where it's warm enough. We don't have woolly mammoths walking around here in New England. So each of the peaks would be an interglacial, and then each of the valleys, in terms of carbon dioxide in those bubbles, would be a glacial maximum. When here in New England and here in New Hampshire, coastal New Hampshire, we actually had 2 miles of ice sitting on top of us, and that would be over here. This is the previous glacial cycle, about 110,000 years ago. It was like today, but just a short period of time ago, it was 2 miles of ice on top of us. So glacial maximum, glacial minimum. We're in a current glacial minimum today. And this is where our carbon dioxide concentrations are. As of yesterday, our carbon dioxide concentration was 417 parts per million. And you can see this is clearly off the scale. This is clearly very different than anything we saw in the ice bubbles relative to the past. And these ice cores go back almost 2 million years, and we have students making the measurements right now to find out what carbon dioxide levels were back then. So we're off the scale in terms of parts per million carbon dioxide. I would point out that there are carbon dioxide isotopes, one with carbon-12 and one with carbon-13. And I haven't talked anything about that, but that's essentially the mass or the atomic weight of carbon. And carbon-12 is lighter than carbon-13. And carbon-12 is taken in preferentially by vegetation. Just because carbon-12 is lighter, it's got a more rapid diffusion rate in through the stomates, gets incorporated into the wood of the tree, and that sort of thing. Carbon-13 is heavy carbon and heavy carbon dioxide, and plants don't select much of that. And that rapid rise that we see in carbon dioxide, up to 417 parts per million, most of that is light carbon, and that's because the fossil fuels that were burned to release that carbon ended up being plants back geologically a long time ago. And so as a result, that coal that was burned or the petroleum that was burned was very rich in light carbon dioxide because it was plants. And now it's burned and it's become part of our atmosphere. So again, we know where that carbon dioxide is coming from. There really isn't any debate about that. Turns out that sea ice becomes an important factor, and especially polar sea ice. If we've got a lot of polar ice, then 90% of sunlight is reflected back into space. On the other hand, if that sunlight hits open water or ice-free land, 90% is absorbed and then re-radiated back into the atmosphere and trapped there by the greenhouse gases. So you probably all know that our North Polar cap, ice cap, is melting dramatically. This is what it looked like measured by science, by satellites rather, in September of 1987. Here's 97. Here is 07. And I was not able to find a graphic showing you what it's like today. I'll just move back. You can see here is Asia. Here is Greenland. And here's the ice back in 2007. It's not quite the so-called Northwest Passage is not quite free of ice. But here, this is reoriented, but this is now Greenland. This is Asia over here, and you can see there's a whole lot of open water. And this would have been in September of 2012, 2020 modeled together. So things are really changing. Turns out that our climate today is seemingly a little unsteady. Is that melting of the Arctic and the open water there, is that related to the weird weather we're having? This past summer, we had periods of rain and fairly heavy rain, and then dry, and then another pattern of heavy rain. When I grew up in Vermont back in the 50s, we didn't have torrential downpours. It was kind of more gentle soaking rain. All of that has changed. This is a graphic showing a massive amount of snow across the northern part of the country. The really bright areas would be cities, that sort of thing. So is there a connection? And it turns out that if we look at land surface temperature anomalies, changes in North America, we see they are linked to unusual warming in the Arctic. You see it up there in Alaska, and the loss of sea ice. And so that is a thing that has happened recently. Turns out that we have multiple jet streams. There's one called the polar jet stream. And that's the one that we are affected by. You can imagine that arrow is right over New Hampshire. But then we also have subtropical jets, both northern hemisphere, southern hemisphere. And it turns out that there are wrinkles in the polar jet stream, the North Polar jet stream, that are called Rossby waves. And these are patterns, and that jet stream is rotating around the surface of the planet. The planet itself is rotating. And it turns out that if we look at kind of the normal situation here, you don't have a lot of wrinkles. Over here, we've got more wrinkles that are developing, and this would be a high-pressure system. This would be a low-pressure system. Here we have kind of an exaggerated wrinkling, and development of Rossby waves. And we fortunately go back to the normal condition, but over the last 10 years, we've just been in this wrinkled Rossby wave situation. And that's attributed largely to the reduction of polar ice and open water. So if you've been wondering why the weather is so changing dramatically, it's in large part the result of that open water in the Arctic. This just shows the same sort of thing, where the deep blue features are. That would be a low-pressure system, and then the lighter areas between them would be the high-pressure system. And on the left, that would be with wrinkled Rossby waves, and over on the right, that's kind of a more normal situation that we think we must have been in back in the 50s and 60s, but we weren't measuring it then. So in fact, we didn't know about that back in those days. Okay, so let's talk a little bit about the politics. This is the Paris Climate Agreement, sometimes called the Paris Climate Accord, a global consensus. This is on in 2016, Earth Day. This was one of the happiest days of my life. I was very excited that the world finally accepted that there was a global consensus and we had to do something about it. John Kerry was Secretary of State at the time. He's holding his granddaughter in his arms as he signs that accord. I thought, wow, this is great. We need to do this. Here are the Paris Accord Agreement goals. Set a long-term goal of keeping global average temperatures well below 2 degrees Celsius or 3.6 degrees Fahrenheit. We're not going to reach that goal. We're already well on the way to being at 2 degrees Celsius. And that would be a change in temperature from where we are today back over pre-industrial levels. Aim to limit the increase to 1.5 degrees Celsius. It's really important to do that to reduce the impacts of climate change. We need to have a global emission of greenhouse gases to peak as soon as possible, preferably 2050, and then essentially eliminating certainly carbon dioxide and methane. We hope that we can do that, but I'm not too hopeful that we'll reach that particular goal. And then we need to just continue to support that rapid reduction of greenhouse gases based on the best possible science. These were heady times. Unfortunately, climate change has become a very bitter political problem, and it became so much worse after the 2016 election. I want to point out that it really is important that you know where you're getting your climate science news. CNN, there on the left, 30% misleading, but 70% accurate in terms of climate science. Fox News, a dramatic difference. Here is MSNBC. They tend to have the most accurate climate news. Very, very impressive. So again, where you get your news about science and climate change depends on perhaps the network you're watching. It also turns out that you can see that in terms of accurate and misleading, seeing that MSNBC really wins the day. Turns out that 22 senators from these states wrote letters to President Trump. The really dark red states would be where 2 senators are. The pink states would be where one of the senators wrote, and supporting the withdrawal from the Paris Climate Agreement. This was one of the saddest days of my life when this happened. We all know that. I'm not trying to overemphasize political differences, but boy, what a change from President Obama to President Trump, just day and night. Also turns out that President Trump selected a number of people that were climate deniers to serve in his cabinet, head his agencies. Got Ted Cruz makes the statement that there has been no significant global warming for the past 18 years. You wonder what planet he's living on. And then in the 70s, we were told there was global cooling. Big problem, and then it faded. Well, that's true. Remember in the 70s, that was that stabilizing period, and we thought we might be entering the next ice age. That was a concern, but of course, the rapid warming in the latter half of the 20th century and continuing today, we're not worried about that anymore. This was a colleague of mine. She submitted a proposal to NASA to do some climate research, and she received this letter. It turns out, I've been asked to contact you to update the wording in your proposal abstract to remove words such as global warming and climate change. This is being asked as we have to meet the president's budget language restrictions. So the science was being muzzled. We couldn't use the term climate change, couldn't use the term global warming. That was a no-no. We also have things here, Scott Pruitt. We saw he was the EPA administrator. We know that humans have most flourished during times of warming trends. I think there are assumptions made about the climate as it's warming, and this is not necessarily a bad thing. Just looking at the tornado that ran through, 6 different states, starting with Kentucky, the huge damage there. This warming is a bad thing. And then that statement from Tim Wahlberg, if climate change is a real problem, God will take care of it. Well, God helps those who help themselves, and so we need to be serious about this. And then, as if withdrawing from the Paris Accord was a sad day, just when you think things can't get worse, here's that insurrection at the Capitol. Just unbelievable. Look at all of those people. Wow, and the damage they did. So the question is, how do we get to be so divided? It wasn't like this when I was growing up. I'm sure those of you that are old enough to just remember the Reagan years and the Clinton years, we cooperated with one another. I was in Washington, D.C. for a year working on Al Gore's Globe program, a K-12 science education program. And I remember very, very well sitting down and meeting with Al Gore, for one, Ted Kennedy, several others, and there was a graciousness and an importance to being in the Senate, being in the House of Representatives. Today, it's very clear that one side will make certain that the other side can't do anything. And it's crazy. The good news is, even in spite of that division, we end up having municipalities, towns, cities, states taking action. Turns out my sister lives in Vermont, and I drive Route 89 from Durham, New Hampshire up to Barre, Vermont on a fairly regular basis. And there are all of these solar farms that you see along the way. That's such a good idea, great idea. That solar energy is free. The panels aren't free, but once they're installed, you're getting energy for free. Really a positive thing. We also have to stand up for science. I've been part of many marches in support of science, and in particular science of climate change. This is just some examples. This is what a scientist looks like. I'm with her. I mean, these have an impact. I'd like to see them have more of an impact, but I'm in the back row there. AGU, it's a meeting, the American Geophysical Union, a meeting going on right now. I'm not there in New Orleans, largely because of COVID and concerns about COVID. But if I were, there would be these rallies going on supporting Stand Up for Science. Good thing about science is that it's true, whether or not you believe it. So remember, I mentioned that early on. Earth Day demonstrations have been dramatic, and especially after 2016, which was the hottest year on record. Earth Day activities, very dramatic around the planet. All good news. This is one of the t-shirts, or excuse me, sweatshirts that I wear. The Earth is not flat. Vaccines work. Boy, is that appropriate today. We've been to the moon. There are huge numbers of people that don't believe we did that. Frightening. Chemtrails, you know, the vapor trails you see from aircraft flying overhead. There's a conspiracy theory that that's a government attempt to sow toxic chemicals from these aircraft. Crazy. They aren't a thing. Climate change is real. Stand up for science. Words to live by. We've talked the last time about a suite of Earth-orbiting satellites that are used to observe the Earth on a daily basis and monitoring day after day after day, looking at weather patterns, looking at vegetation, of course, health of vegetation, ice extent, etc. We also mentioned NASA's A-Train, series of satellites all in the same orbit, separated by just minutes apart, measuring, again, the North Pole, the South Pole, and everything in between. This is one of NASA's latest satellites. It's an orbiting carbon observatory called OCO, and it's actually measuring carbon dioxide levels and methane levels. And I love the logo. Turns out that carbon in a carbon dioxide molecule, carbon is the central atom, and oxygen, there are two of them on either side. Very clever. This is a graphic showing Earth from space. And on the left-hand side, this is the Earth at night. We can see where most people live. Again, the lights showing us where the concentration of people and industry and cars and all of that are, compared with anything west of the Mississippi. And then this is an OCO, an orbiting carbon observatory data set, showing that that's where the greatest amount of carbon dioxide is. And this would be the Indiana, Ohio, where a lot of the pollution is coming from. So we live in a wonderful time. We've got wonderful tools to study this. We just need to get a public commitment to being involved. Back during the Trump administration, 5 of NASA's Earth, they have 6 Earth science missions. 5 of those were slated for the chopping block because they ended up involving studying of all things climate change. And fortunately, 4 of those were reinstated by Congress. So again, there is hope. There is a move afoot to send astronauts to Mars. This is the Orion capsule that is going to take 4 astronauts to Mars. Keep in mind that trip is going to take 6 to 8 months. Can you imagine being in that capsule for 6 to 8 months? It would be unbelievable. But that's the plans, and the idea is we'll have humans orbiting Mars by early 2030s and actually setting foot on Mars in the mid-2030s. And the real question is Mars really worth it? This is another mission that NASA is developing to one of the moons of Jupiter called Europa. It's an icy moon. The surface here you see is all ice. There are tension cracks. That's what the dark areas are. And is that more important than Earth? I happen to be a big supporter of space travel. I told you that, I think, the last time we talked. But I'm not sure it's that important, especially if we need to develop a sustainable condition on our planet. There's got to be a mix of environment, economy, and society. And we're not doing a very good job of that at this point. And a healthy environment is prerequisite for a healthy economy. They go hand in hand. It can't be one or the other. So I'm just going to finish by this statement. In the latest IPCC report, Intergovernmental Panel on Climate Change report, human activities are estimated to have already caused approximately 1 degree Celsius warming, and that's compared with pre-industrial levels, 1.8 degrees Fahrenheit. And that global warming is likely to reach 1.5 degrees Celsius between 2030 and 2050. Well, that's no longer the case. This was what was written back in 2018. And now we've already reached that point. It's not 2030, it's 2021. So we've just got to do a better job. There is no planet B. And what the future will be, that'll depend on the decisions that we make today, because that will shape tomorrow. And hopefully in this talk you've learned something about the science behind climate change. You've seen the disastrous effect on attempting to do anything about it that are political, totally political. No debate in the scientific community. It's only a debate in the political arena. And so I hope you have some questions about this. We'll be meeting to talk about this, and I look forward to hearing any questions you might have. So thank you very much.
Well, I hope you've enjoyed this presentation and will join us for the next two presentations on March 2nd and March 9th. They have slightly different focus points. And Professor Rock, we have a couple of questions here from participants. I'll read them and then you can respond as appropriate. Jonathan Ring says, I assume that the ppm greenhouse gas peaks and valleys show northern hemisphere. You mentioned summer and winter. He says the bulk mass of the Earth, of course, is northern hemisphere.
That is absolutely correct. And it turns out that if you look at that peaks and valleys pattern, it's exactly the opposite in the southern hemisphere. And unfortunately, most of the land mass is in the northern hemisphere. Most of the population is in the northern hemisphere. So that's why I focused on that one particular peak and valley pattern. But it's exactly the opposite in the southern hemisphere. Just there's not a lot of CO2 coming from the southern hemisphere, and there's a lot of CO2 being absorbed by the Amazon and the forests in Africa. So, but excellent point.
Yeah. And an anonymous attendee says, asks, what are the most sensitive metrics for monitoring climate change?
Good question. Certainly looking at temperature is very, very important. And as we've seen in the presentation, the temperature and the essentially the CO2 levels have fallen right in lockstep. Prior to the Industrial Revolution in the 1750s, CO2 was level. temperatures varied, but those were based on natural processes, solar activity, volcanic aerosols, and that sort of thing. But with the Industrial Revolution, the emission of carbon dioxide just skyrocketed, and that has brought about a change in the peaks of carbon dioxide, but also of methane and nitrogen oxides. And each of those is a greenhouse gas. So it's not surprising that we're in a situation where our planet is getting warmer and warmer and warmer. The last 5 decades, each of those decades are warmer than the preceding decade. And so there's a clear upward trend. And the 6 hottest years on record are from 2016 on. And 2021, 6th hottest year. We're in a situation where we really need to address the problem and measure the amount of CO2 reductions. But then you've got to do the same thing for methane, and that's a challenge.
Yeah.
So those are the metrics I'd look at.
Excellent. This series is brought to you by the First Unitarian Universalist Society of Exeter, the Unitarian Universalist Church in Exeter, and more specifically, the Social Justice Committee and the Forest and Climate Change Affinity Group. And so this really was enabled by a grant from a wonderful donor who recently passed away, Ingeborg Locke. So this is part of the Ingeborg Locke Opportunity Grant that is funding this effort. So I do have a couple of questions from the people who helped put this program together, from the Social Justice Committee and the Forest and Climate Change Affinity Group. Is there agreement among scientists regarding how much we can rely on forests to stabilize climate?
Yeah. The answer is yes. And that's based on geologic data looking at hundreds of millions of years ago. And when the planet was first formed, it was very, very hot. And that period, 1.5 billion years in length, was called the Hadean for Hades. It was hell, and very, very warm. And our planet had no oxygen at the time. It was all carbon dioxide. And then you get to the period where life had evolved in a period known as the post-Cambrian. Don't need to get into the details, but essentially going back 600 million years. Initially, all life was in the ocean, and much of it was photosynthetic, algae and that sort of thing, fish, mollusks. But at the end of the Devonian, life crawled up onto the surface of the land. And the land was absolutely barren. I mentioned in this presentation the moon, and boring as hell, Hadean hell. And it turns out that vegetation evolved at that point and started producing forests, trees. And the CO2 levels dropped dramatically. And it's accepted that the reason of that drop, dramatic drop, was the forests. So that's one piece. The forests are also producing oxygen, and so prior to this, there was very little oxygen, just what was produced by the algae in the oceans. But once the trees came on, huge increases in oxygen, huge decreases in carbon dioxide. So there's really no doubt the role that forests can play. Now, looking at today's Earth, we're not dealing with a barren landscape.
Right.
We've got all kinds of urban development. We've got agricultural development. We're cutting down the trees almost as rapidly as we can to make room for agriculture. We're in a bad situation, and if the current continents were covered, totally covered with forests, we wouldn't have this climate change issue. But of course, not all of the land surfaces are covered with forests. In fact, only about 20%, 30% of the land surfaces are heavily forested. And so to address climate change, we really need to let trees do their job. And their job is they do it for free.
Yeah, yeah. We have another question coming in from Gwen and Steve Kenny. Is it too late at this point to plant trees and have that make a difference?
No. We're getting to the point which would be called a tipping point, where ramping up the forests, it will be too late. And that's perhaps, I've heard estimates from 10 to 30 years from now. Planting trees is very important, and planting the right trees is very important. Evergreens are a good bet because they're photosynthetic year-round, or have the potential of being photosynthetic year-round. Oak trees are great because they're cell walls in the wood. And that's where the carbon dioxide is gone, making the cell walls. Perfect. You also want rapidly growing trees, and birch and poplar, alder, those are very rapidly growing trees. So the sooner we can get the right kind of trees planted and extensively planted, the better our chances of combating climate change.
Great. Another question from Skip Berrien. He says, thank you for the information, the scientific data. The presentation is very informative. In terms of policy, it may be that transportation is a significant contributor to greenhouse gas emissions.
Absolutely.
Should lowering greenhouse gas emissions in the transportation sector be left to market forces, electric cars, et cetera, or can state and federal policies incentivize the use of more efficient vehicles?
I would like to see the state and federal mandating policies. President Obama, towards the end of his second term, instituted policy that would lead to electric automobiles. And specifically, the source of the electricity needs to be solar, wind, water, and not burning coal.
Right.
I happen to drive a Prius Prime, getting 183 miles per gallon, but I plug it in often. And our energy source states that 75% of the energy that they produce, the electricity they produce, comes from renewable sources. So where you get your electricity, but we need to do away with internal combustion engines.
We have an initiative that's been brought forward by the Energy Committee in the town of Exeter, and people will be voting on this in the March 8th thing to be able to have options as to where our electricity will come from. You can choose more renewables, hopefully at a reasonable cost, and maybe even lower than the regular source, I'm not sure.
Yeah.
But that's coming up for voting in Exeter, and I read that recently Portsmouth signed on to the initiative for having alternatives, and I don't know where Durham stands on this.
Durham has a solar farm.
Okay.
But that's the local production of electricity.
Right.
Most of us get electricity from something other than Durham.
Unitil or...
Yeah.
Another question here from the Social Justice Committee. Trees remove carbon dioxide from the atmosphere. Are there alternatives to trees which can supplement what trees may not be able to accomplish?
Well, there's active research on carbon capture and storage mechanisms. I was in Iceland last July, and they have a program whereby CO2 is removed essentially at the source from power plants and that sort of thing, and pumped down into the bedrock. And
For storage?
Yeah, storage. And the carbon becomes calcium carbonate, a mineral.
Yeah.
And it works very well in a kind of a closed system. And I think of Iceland as essentially a closed system. Doing that on a global scale is going to take a lot of time, a lot of research, and a lot of money.
Yeah.
And I always like to remind people that trees do their job for free. So keep that in mind. However, this idea of active carbon capture and storage, they're making good progress on that, and it will be more efficient than trees.
Since both of us have been professional educators in our careers, here's a question that relates to that. What systemic changes do you think are worth considering for U.S. for U.S. public education at all levels to address our present and future environmental problems?
Well, first of all, we don't want to ignore the problem. Very often in education, part of the problem is teachers and they're feeling comfortable with the material that they are presenting and asking their students to learn. And climate change has not gotten to the point where it's a comfortable discussion that can be held in a classroom. And unfortunately, as we mentioned in the presentation, we have become so divided. If you're from a red state, you probably got a very different type of curriculum from if you're from a blue state. And so we've got to address those issues. And it's not going to be easy, but we have to do it.
And of course, here in New Hampshire, we have legislation on the books to not allow teachers to teach anything that's a divisive concept. So, and that's happening all over the country.
Yes, it is.
One more question here. What are some opportunities associated with climate change, science, and education that you feel may already have been missed? What are some new approaches to consider? And how or on what basis can we as concerned citizens be positive and motivated while working on this daunting task? So what's been missed and new approaches to consider?
Yeah. And again, I just go back to the division that we find ourselves in. It's very difficult to get certain things taught in a high school curriculum or a middle school curriculum. When I was an active faculty member at the University of New Hampshire, I developed a program called Forest Watch. And Forest Watch looked at white pine, and every school has a white pine tree nearby, probably more than one. And white pine is a very sensitive bioindicator for exposure to ground level ozone or smog. And you can teach a kindergartner to recognize the little yellow spots that are on the needle of white pine that are an indication of ground level ozone exposure. And that program went on for 23 years, 24 years until I retired. And teachers loved it. There was no question about looking at white pine needles with a little hand magnifier or a microscope, so it wasn't divisive. And one of the major points was when the pine trees are healthier, they're absorbing more carbon. We didn't mention climate change. We didn't mention global warming. So there are ways of doing it. You just have to figure out how best to do it. And but got to let the trees do their job.
Yeah, yeah. One more question here. Can New England forests be managed or adapted by humans, or are we better leaving it to the cycles of nature which we are experiencing?
Very good question. In terms of active regrowth, I think of pine plantations that are destined to make pulp, paper,
yeah.
And that sort of thing. Those are fairly fast-growing trees. They're being fertilized at some expense, but there's commercial value to them. And if we could get into a situation where we select the right kind of trees and get them growing actively, it'll make a difference.
All right. Any final words you want to share with our viewers?
No, I hope this wasn't too much science. I also hope that you learned at least one new thing tonight, and we will be having 2 more of these presentations, and I look forward to helping people understand the value of forests.
Yeah. Yeah, the next one is going to be The Secret Life of Trees, and that goes into the morphology and physiology of trees and their parts. And then the final one will be on March 9th, Monitoring Forest Health from Orbit, from Space. And that's something you spent much of your professional life working on.
Yes, yeah. I'd just mention that The Secret Life of Trees, I think most everyone, I certainly did, see trees as passive bystanders. They're there, and they're a forest. And if you want to build something, you cut the forest down, that sort of idea. Turns out that trees, and this will come through in The Secret Life of Trees, are in communication with one another. And they're in communication underground. Their roots contain beneficial fungi that form a network underground. And the trees are communicating with one another. They're supporting the young seedlings and saplings that are coming up. They notify one another when insects are attacking, or, we didn't know this 20 years ago,
Right.
and we know it now.
Yeah.
And so it's really important to see trees and forests as active participants in the landscape. They're not just there to be green.
Yeah. Thank you very much, and thank you to our viewing audience. I hope you all did learn at least one new thing, and we hope to have you join us for the future programs. Thanks to Bob Glowacki for all the technical assistance he provided to put this on through our Channel 98, Exeter TV. One of the programs, I think it's the next one, will be also shown on Channel 13, which is the Exeter cable TV station. The surrounding towns of Stratham, Newfields, Brentwood, East Kingston, and Kensington can watch. The Exeter residents are restricted to just being the ones that can view Channel 98. So thanks again, appreciate it, and we look forward to seeing you in the future programs.
Great.